Good morning and welcome to today's computer vision lecture. We will start with a quick revision of what we did last week. And in case you did not join last week, the live lecture, you know we have the recording in YouTube. So last week we started looking into image sequences. We discussed that motion is something we come across very often in computer vision, like when we want to track objects, track features, uh, reconstruct surfaces, scene dynamics. And there could be lots of applications like collision detection, motion stabilization, and so forth. So we deal with motion quite a lot in computer vision. And for that, we need to look into image sequences, not just static images, but actually a sequence of images. And we started looking initially at temporal models, and the temporal models we discussed are highly generic. They work for all sorts of sequential data, not just vision data. Here, what we would do is we would probably just put features into these models, so features that we compute before from the images, and we would put these features into the temporal models. And we saw a couple of examples, and we saw these examples have something in common. Concretely, we wanted to do state estimation or filtering, and then we built our framework that we look at states and observations. We looked at time slices. We looked at the transition model, the tensor model, the sensor model. We made the Markov assumption, and then step by step uh, looked into our first example, which was about rain, which is the unknown variable, and we have the known variable that we can measure is the umbrella one, and we try to estimate or filter rain. We looked at that and we described filtering in greater detail. What we need is the Bayes theorem, very important foundation for lots of courses in your AI program. And so we also need it here for the temporal models. And we looked at how we can express filtering. We looked at an example about the rain and umbrella, and then we looked at a couple of other tasks like prediction and smoothing, as well as the most likely explanation and learning. Learning means learning these transitions in the models, and that's something we would typically do with the EM algorithm. Now, these models are highly generic, and we can look at more concrete filters like the Kalman filter, which allows us to estimate state variables from noisy observations over time, and our variables are continuous. If the variables were discrete, we would need a hidden Markov model. So these two are related, yet working somewhat differently. And then we introduced the Kalman filter, for which we need these linear Gaussian distributions. So we quickly revised the Gaussian distribution in 1D and multiple dimensions, and then step by step build the Kalman filter in a one-dimensional case. And we see the beauty is eventually to update the mean as well as the variance. And this can be done super well and super easily in the Kalman filter because we take advantage of completing the square. Then we saw we can extend the Kalman filter to more dimensions if we wish, and we can express all of this in terms of linear algebra operations. But this looks more complex than it is. It's just a generalization of these two update equations from before. Looked at more examples, and there are also lots of videos visualizing the Kalman filter if you wish, and quite some students every year use the Kalman filter for a project. Not all, obviously, but some. And uh, when you want to use the Kalman filter, you don't need to implement it from scratch. You're most welcome to implement it from scratch, but there are also libraries that you can use and then probably have a more efficient implementation. Then we also looked at the correspondence problem, and the correspondence problem is the problem of ascertaining which parts of one image correspond to which parts of another image. And we will now um, look at the so-called optical flow, and the correspondence problem is a building block in the optical flow. And the optical flow, concretely, we have two images which are subsequent in time, and we want to infer something in it. Um, I also received quite a few emails about the projects in this course. I'll talk about the projects at the end of today's lecture. So we'll first do the lecture. We finish quickly the image sequences. Then we will look at robot vision, and we will then look at an outlook, and probably we finish the remaining content today. And once we're done with that, I will say at the very end a couple of things about the project. So in the optical flow, you can imagine we have the following situation. We have an image, which is this one here, at time t, and we will have now one time step in the future. And what we see is we have motion in this image sequence from one image to the other. And because, for example, objects move, whatever. And with the optical flow, we want to be able to describe this motion of objects and surfaces in edges. And we start looking at a couple of examples to first see what the optical flow is about, and then we will actually start describing it. Motion happens when objects, for example, move in an image sequence, but sometimes there may even not be motion, but it could appear that there's motion in an image sequence because, for example, when lighting changes, so the illumination changes, and this may create the impression that there was actual motion in the image sequence. In fact, the illumination changed, but not the objects moved. This is something that we can also explore and make some discretion about. So the optical flow, you can imagine it as something like this. So we have an image here of these football players coming in, and we have an image sequence, say one image now and one image maybe 1 second later. And we have various dots in here in this grid throughout this image. And we want to determine how much movements are around that pixel from one image to the next one. So let's say one image per second. And what we see up here, there's maybe very little motion to no motion because someone is just sitting there. There could be a little bit of motion because maybe one of the people sitting there raises a hand or moves a head, whatever. So sometimes there can be some motion up here, but most of the motion in the image is here where these football players, they're coming in and they are walking from left to right. So we see that just 1 second later, the features or the part of the object where this pixel is actually moved to about here. So what this visualizes to us is motion in the image. And we can describe this motion in the image sequence with the optical flow. The optical flow makes a couple of assumptions. First of all, it assumes brightness constancy. So we project or we want to look at one point from one image to the next one in the image sequence, but we assume that pixel or that small area that we are looking at is actually not or keeps its brightness. So the brightness does not change. If we did not assume that, all of this would become more complex. We assume some pixel moves, but its brightness has not changed. We also assume small motions, so points do not move very far from one image to the next one in the sequence. And we also assume spatial coherence, so points move similar to their immediate neighbors. So points that are super far away, they move different, but the immediate ones that are close, they move similarly. And for showing you what the key idea of the optical flow is, I will switch to my whiteboard. So we will now use a notation and do some things that are actually a little bit similar to what we did in the Harris corner detector. We are obviously pursuing a totally different goal with the Harris corner detector. We want to find corners. Now we want to know the optical flow, but some of the manipulations we are doing, they would be, at least some of the initial steps will be quite similar to some of the work you have seen in the Harris corner detector. So we want to express the intensity as a pixel now as the intensity of x and y, so coordinates x and y. We used exactly such a scheme also when we looked at the Harris corner detector. But now we also want to include the time t because we're now looking at image sequences. And we want to consider the intensity after a small change in time. So, and that would be a new position. So we would have I, we will add something on top of X, we will add something on top of Y and our T. And what we want to do concretely is we will add a change of X on top. So delta X, because from one image to the next one in the sequence, that pixel has moved along X. It has also moved along Y, and obviously some time has passed, so we're adding on top delta T. And I've noticed the screen share just stopped working. I'm sorry. I'm personally also bothered that there are always issues with the screen share. This is something that has declined with Zoom in recent years, but I will still stick to the Zoom because all the other things are working well. And if I switch to a different tool, it will cause new problems. So, but I hope these screen share issues will get fixed with the next Zoom update. Now we had this brightness constancy in which we said we expect the brightness of the pixel to not change from one frame to the next one. So we will come up with the following identity. We say our intensity at x, y at time t is the same as the intensity when we go to the next frame. So we said x would change, so x plus delta x, y plus delta y, and the time plus delta time. We said this is the same. This is the brightness constancy assumption that we are making. So just highlighting this. You can also put a name on top, and we say this is the brightness constancy. And now we want to simplify this a little bit. So we need to apply to our next one here, the Taylor series. Taylor series is something we also saw when we studied the Harris corner detector, and we saw how it works for multiple variables. So we will do the Taylor series, and then we will get, so we have the intensity at x plus delta x, y plus delta y, and the time plus delta time. And if we apply the Taylor series or Taylor expansion to this, what we will get is we'll have the intensity at x, y, and t, plus we will have a couple of partial derivatives. I will write out these partial derivatives in a different color because we will need them later. So we need the partial derivative at the intensity along x times delta x plus the partial derivative of the intensity along y times delta y. We will also have this for the time. So partial derivative of the intensity along t times delta t, plus we have some higher order terms, as we could continue this forever, but we don't care about the higher order terms. So we will ignore the higher order terms. And because we've said that we're doing the Taylor expansion, so just remember we applied Taylor to this one up here. So we said when we apply Taylor to this equal its Taylor expansion. And we will ignore the higher order terms. And what we can eventually, what eventually follows from this Taylor expansion is, can say our three partial derivatives, so the partial derivative along the, or of the intensity along x times delta x plus the partial derivative of the intensity along y times delta y plus the partial derivative of the intensity along the time times delta x is 0. This is a consequence, and we will now divide by delta t. So we divide by delta t. And that means we have the partial derivative of the intensity along x times we had the delta x, and now put here we divide by delta t, and we have the partial derivative of the intensity along y times delta y. We divide by the chain by delta t, and then we have the partial derivative of the intensity along t times delta t divided by delta t. And this is 0. And then obviously these two terms just cancel out. And we will now simplify this notation a little bit. And we're using a notation that we had also used for the Harris corner detector. We will write out these terms now in a slightly different way. And we will say that we have this partial derivative of the intensity along x times Vx. I'll tell you soon why we're calling this Vx, but we're doing the same for the partial derivative of the intensity along y times Vy plus the partial derivative of the intensity along t. And now our Vx, Vy, and x and y are the components of the velocity or optical flow of the intensity. And these partial derivatives that we still have here, so putting these partial derivatives in green, we said all of this is equal 0. And these partial derivatives of the image at x, y, and t in these corresponding directions. And we can still amend the notation a little bit just to make it look simpler, so we get rid of always writing out explicitly these partial derivatives. So we can say this is Ix, and you have our Vx from above, plus our Iy times Vy. We can say that this is minus It. Because we have just divided by the minus It. I'm just putting some reference here that we know where these terms come from. Using these i's and v's, it just looks a little bit simpler because we don't need to write out explicitly always these fractions for the delta x divided by delta t or these partial derivatives. And now we can rewrite, this refers here to the optical flow, we can rewrite it again in a vector notation because we can say that this is nabla I, so the gradient of I times v, and v is a vector, which is for the vx and vy, and this is equal to minus it. So what does this mean now? This formula or this equation refers to the optical flow. The only problem is that this is an equation in two unknowns, and we are unable to solve it as such. And this problem that we have an equation in two unknowns that we cannot solve as such is called, or this refers to the so-called aperture problem. The aperture problem is something we will visualize in a moment. And we want to know actually now the optical flow. But in order to find that optical flow, we need another set of equations that we need to solve as a constraint. And we need to add some constraints because this one here is not solvable as such because we have too many unknowns. So the optical flow is a generic approach, but we need to make some concrete assumptions about the optical flow. And for that, there are numerous proposals about what extra constraints we're adding here in order to make this solvable. And this is what I will show you now. All I have written down is also available in the slides, well formatted. So we looked at the Taylor expansion, and then step by step, we refined the optical flow equation. And we will now come to the aperture problem. So the aperture problem is something I will visualize for you in a moment. And what we will see is it appears that the grating is moving down and to the right, but we will test this now. And for this, I'm switching to the browser. I'll change the screen share very soon. So can also zoom in. So what you see here is we have this grating and it seems to appear to be moving down and to the right. But that's only what it appears to be. It could also be moving in any other direction, such as only down, only to the right, whatever. So just by having this visualization here, we are unable to determine unless we see the end bars and they become visible in the aperture. And this is exactly a visualization of the equation from before that becomes unsolvable because we have too many unknowns. So what we need to do is we need to make some more assumptions. And for this, there are lots of different concrete optical flow methods that make more assumptions. And I have also a reference to this website here, which explains and visualizes various optical flow implementations quite well, because we need to make more assumptions and we need to add some more constraints in order for that equation to be solvable so we can describe or calculate the optical flow. The beginning of this blog post is what we just did. We looked at the Taylor expansion, and then there are different optical flow implementations like a sparse or a dense optical flow, because they're adding some more constraints. And in this website, there are also some code examples in case you want to explore them and test them. And there are more concrete insights about various optical flow implementations if you wish. But this is one of your homework to look at, and it also comes with some code examples that you can easily run in case you wish to learn more about concrete optical flows. So the reference is also in here. But the main part of this course was the Kalman filter. And this one is something that quite a lot of students use every year. Some students I've also seen implementing optical flow. And if you want to learn more about the optical flow, take a look at the website I have just shown you. Now we have 2 chapters left. And actually, we have already studied quite a lot now in these few lectures about computer vision. What would now come are usually an outlook with a couple of advanced topics that are interesting to study. But before we do that, we will look a little bit at mobile robotics, because quite some of you got a robot because you're interested in a robot vision project. Maybe you can just signal to me here in the chat or with a reaction as a thumbs up, whatever positive reaction. If you got a robot, if you want to work on a robot vision project, and maybe a different reaction in case you don't. So actually more students that sent a positive reaction than the ones who sent now there are more negative reactions. So robots are messy and robots lead to more work, but eventually it's also more rewarding. It's a different learning experience. And because some of you are doing a robot vision project, it's probably helpful to provide you with some insights about mobile robotics. And once we have done that, we will look at the outlook with a couple of more advanced vision topics. So we will look at motion of mobile robots in 2D. We'll look at some of the physics or some of the way to describe the movements. We will also look at sensors. We will look at probabilistic robots because our robots deal with a highly probabilistic environment, and sensors are probabilistic. So we see how we can plug this in. And we will then study concretely the so-called particle filters, which help our robots to determine where they are actually in a map. And then we will also look at SLAM, which is simultaneous localization and mapping. So the robot is able not just to determine where it is in a map, which is the localization, but it's also able to learn a map in parallel. And when I started this course a few years ago, I started teaching this course 5 years ago for the first time. I felt if you want to do a vision project on your computer and show us some algorithms, that's cool. But if you want a robot, that's also great. So we ordered a couple of robots a few years ago. And what we bought at that time is the Jetson Nano developer kit. We also have other robots now in the deep learning lab. So we still have this platform, but we will slowly replace it because the GPUs are not up to date anymore. But there are other robots as well that Mr. Rankel showed you. And when you look at this Jetson Nano developer kit, there are lots of items in it, and you can assemble the robot on your own. For the ones of you who picked the robot, did anyone assemble the robot on your own from a new kit? If so, positive reaction. If you got a robot that was assembled already, send me a different reaction, because this was one of the tasks of the students in the first few years when we bought more and more of these kits, that someone had to actually assemble the robots. But then over time, I guess most of the kits that we have are actually assembled, and you can probably just pick a robot that is assembled already. These robots also tend to break over time, that maybe some sensors break on one of the wheels. If any of your robot breaks during the project, no problem. Just get in touch with Mr. Runkel, and he'll be happy to give you some spare parts. And every year, some of the robots died. We had all sorts of issues with, I don't know, a malfunctioning power cable that grilled some of the robots and this kind of stuff. So it's all happened, but it's all not too expensive. And we have lots of spare parts for you to replace um, those broken components if you wish. And what's interesting in here is, so we have a board, or actually two boards that we need to connect. We put a GPU on one of the boards plus some batteries. So all of this is just a robot with a GPU. And what's interesting is this camera here that you mount on the robot, and it's here on the front. So, and the good thing is you have a GPU on the robot. So you can compute, you can do your computer vision on the edge if you wish, and you don't need an external computer or external server to run these operations. You're welcome to do this if you wish, but then you have extra delays, and you reduce the delays by doing these computations on the edge, and then the robot can drive around. And the platform we have here are two wheels, and I'll show you now some of the underlying maths you need to describe these movements with this kind of robot. Uh, we are using, so this is not a promotion for NVIDIA, but we are using this NVIDIA chatbot platform because there's the NVIDIA Jetson GPU, and then there's the chatbot, which is a robot platform using this Jetson GPU. And there are different vendors, and we bought over the years from multiple vendors this kind of stuff, not just Waveshare. But the good thing is it's relatively low cost to buy these robots, so we could buy a lot of them. So when I started teaching this course, this was during COVID, and we had obviously the issue that you could not be on campus to do your projects on campus. And then we just ordered more of these robots, and the students could take these robots home and work on the projects from at home, which was certainly very helpful. And that's why we bought more low-cost kits rather than super expensive robots, because we only had a limited amount or a limited amount of money we could use to buy these robots. So we rather bought a lot of these low-cost robots so more students could take them home. And now with these mobile robots, um, these robots, they need to have motion, so they need actuators for motion, and they also need sensors for guidance because they somehow need to understand their environment. We will look at different ways how the robot can move and different sensors, but um, our robot will ideally be self-contained, that we have a power source like a battery, we have sensors, do the processing on board. So ideally, the robot would not be somehow connected through a cable because that would limit our abilities. But the robot could still connect to other computers through Wi-Fi, for example. And the chatbot platform that we use offers exactly this. And such a mobile robot needs different competencies. For example, the robot needs to be able to localize where it is in a map. Maybe it even needs to be able to create new maps, unless we run it in a controlled environment for which we have a map already. The robot needs to do path planning, but it also needs obstacle avoidance because there may be obstacles and we don't want the robot to bump into these obstacles. And obviously, these are just the foundations, and then your robot would have on top various tasks that it would do. And every year we have terrific student projects in robot vision. Sometimes it's obviously robots doing localization and mapping, but I've also had students build robots that play pool, billiard, and or pool and um, robots that I don't know could be used for police applications to follow suspects. So over the years, we've had overall really cool projects, but for this, we need some more theory now in order to see how these mobile robots work And later in in your bachelor's, you will have more courses on mobile robotics. So this could be also a preparation for these more advanced courses. There are lots of examples of mobile robots that we deal with every day. For example, field robotics, like exploration robots that explore a different planet or undersea or a polar environment. We could have search and rescue robots, for example, after an earthquake or demining, or I don't know, after clean or for exploring a broken nuclear power plant. For this, robots are also used. You could have applications in mining or transport or container handling. And obviously, there are also lots of military applications, not just unmanned aircraft, but also smaller things like insect robots, land-based pack bots. And obviously, this topic here has become more important in recent years. And now we see lots of applications of military robots in various wars. Um, which is a huge topic and it's controversial and leads to lots of ethical issues. But maybe we rather let robots fight each other than humans, because then we reduce the number of deaths and also impact on civilians. So overall, military applications of robots also have some advantages because it could probably reduce lives lost among humans. But it's a huge topic on its own, and I talk about military applications of AI in the innovation management for AI course, which is one of the courses accompanying your internship next semester. So we'll talk more then about military AI. It's not a focus today. And you could have lots of other applications of robots, like service robots, for example, for vacuum cleaning, lawn mowing, laundry, or all sorts of cleaning robots, medical robots, in particular, surgical robots, hospital delivery, helping elderly in care, transport robots, entertainment robots, and so forth. Like maybe, you remember these RoboCup competitions. I don't know if you've seen them. They were very popular on TV some 20 to 25 years ago, robots fighting each other. But they did not use AI. They only made it look this way, but it was in fact humans using remote controllers to let these robots fight. Um, what I like personally is Lego Mindstorms, because when you build with Lego your own robot, this is low cost and you can easily amend your robot. Unfortunately, Lego had canceled its Mindstorm series at some point. And overall, I found the Lego Mindstorms quite helpful because you had all sorts of sensors and actuators, and you could build your own robot with Lego, which was low cost. From the software side, the Lego Mindstorms was not too great when you wanted to program it, but you could obviously use different software by using a Raspberry Pi to which you would plug in that Lego hardware, like the sensors and actuators, and then it actually worked quite well. And then with your Raspberry Pi, you could run Python and access a GPU that you would add on top of your robot or something like this. So that works quite well then. And that's why I'm actually quite positive about the Lego Mindstorms. Now, when it comes to the mobile robots, we also want autonomy. We could have the lowest degree of autonomy, which means actually no autonomy, which would be a purely remotely operated vehicle, like, for example, in these robot wars or mine clearing, that you would have a human operator that sits further away. Then you can have semi-autonomous robots, for example, like Mars rovers, because Mars is just too far away for real-time teleoperation. So you would give some guidance, but you would also have semi-autonomous behavior, which runs on the edge of the Mars rover. And then you could think about fully autonomous robots, like, for example, the Grand Challenge vehicles. I'll also talk about this soon. Now, there are computing requirements. You need obviously some computer on that robot. And it could be just a CPU, maybe as a very general architecture to run computations. But you can also have more specialized hardware. And in this course, it's a computer vision course. It's not a mobile robotics course. Mobile robotics is only an extension today. So we want to do computer vision, and computer vision can be computationally very expensive. So this is something you would not just run on a embedded CPU, but rather we need something more specialized, like a GPU, an FPGA, or something like this. And 20 years ago, there was a huge breakthrough in autonomous driving. And not sure if you know DARPA, but DARPA is an agency belonging to the US Department of Defense. They aim to explore new technologies early and invest in them, always with the goal of military application at some point. But they invest early and want to explore different technologies. And so they got interested in autonomous driving already more than 20 years ago. And they organized different so-called grand challenges of autonomous cars that needed to complete some course. And there was a DARPA challenge around 2004 or something, which totally failed, and none of the cars made that course. But then 1 year later, so 20 years ago, there was an even larger DARPA challenge that was a 175-mile course through the desert, and autonomous cars competed. And in fact, a few cars completed that. And the one that completed it and won was the Stanford car that you can see here. And it's an autonomous car. You see, in that time, these sensors were obviously much bigger, and in terms of power consumption, it was more difficult. But that one was the first autonomous car that won or that completed that grand challenge. And it took that autonomous car to drive for like 6 hours and 54 minutes through the desert in order to complete that 175-mile course. And this sparked a huge interest in autonomous driving all around the world. And nowadays, we don't have fully autonomous cars yet that we can use all the time for driving, but autonomy levels are going up. For example, Tesla has its autopilot. I bought a new car last year. It's maybe not autonomous yet, but semi-autonomous to some extent. And it's not just autonomous driving that you see now in cars but now every new car that gets sold in the EU since last year in summer needs to offer or needs to come with, it's required, lots of advanced driving assistance systems for collision detection and um, detectors for a dead angle when you turn left or right. So there are lots of features that are required now in new cars. And we're not fully autonomous yet, but we're getting better step by step. It's unclear when we achieve full autonomous driving in maybe complex urban settings, but we're getting better step by step. And a lot of that interest was sparked 20 years ago by um, this DARPA challenge, and the Stanford car actually won. Something I find a little bit sad, in fact, is Volkswagen contributed a lot to that Stanford car through its electronics research laboratory. And they were definitely a pioneer with this stuff. But nowadays, I don't really see Volkswagen anymore as a leader in autonomous or semi-autonomous driving. So it's a real pity because they had a competitive edge 20 years ago, but didn't make much out of it. There are other examples of autonomous robots, for example, cleaning robots, like Dyson invested a lot in this and they built very good ones. When I did my master's in machine learning in London at Imperial College, One of my professors who taught mobile robotics, he was actually helping Dyson to build its autonomous cleaning robot. So that's something that was quite interesting, and we got lots of interesting insights in the lecture from the professor who worked on this kind of stuff. And now we have done the foundations or the introduction to the foundations, and we will now explore robot motion. So we will first describe how mobile robots move. Later, we will look at sensors, and then we'll combine both, and we will include uncertainty. And then we will look at vision again. Now, with a mobile robot, we have various goals. We want speed and acceleration of movements. We want the precision of positioning, but you will later see that it's not fully repeatable. Like if you put a mobile robot on the floor and you want it to take the same angles and the same distance, it's not fully repeatable. So there's some uncertainty because we have uncertainty in our world. Our floor is not fully straight and there's all sorts of issues. So for this later, we need to integrate uncertainty. We also want our mobile robot to be flexible and robust in different conditions. And we also ideally want this to be efficient, especially low power consumption. And today, we will look at so-called coordinate frames. Coordinate frames means we have a 2D world in which, or 3D world in which our robot operates. The mobile robots we are studying today are in 2D, but you could also have one in 3D, like a drone. So if you wish, you could even do a drone project in the computer vision course. I'm not sure if the deep learning lab has any drones available, but maybe some of you have a drone at home. You could also do a drone project as your computer vision project, if you wish. I don't think we had anyone yet doing this, or I think maybe one group in all these years did a drone project. But if you're curious about drones, feel free to do that as well. But the theory we're studying today is for 2D, but can easily be extended to 3D as well. And in this coordinate frame, what we have is we have a robot, and that robot has a certain location, so a certain X and a certain Y coordinate. But the robot also has an angle, so the direction into which the robot is looking. And oftentimes you would say it's a 0-degree angle if the robot just looks along the x-axis. So, and then this robot here looks in this direction. So we have an angle between the where we would have the x-axis as well as or an angle between the x-axis and the direction into which the robot is looking, and that angle would be called theta. If you look at a 3D robot, it's slightly more complex because you have 3 coordinates and more angles, but we're starting with the 2D one today. The robot we are using and that I have talked about before, the Jetson platform, this is one where a robot has 2 motors and we have 1 wheel. So we have a motor here and there, and then we have 1 more wheel here. So just to make sure the robot actually stands straight, because if we only have 2 wheels, the robot would either fall into the one or the opposite direction. Now, if these 2 wheels, they run at equal speeds, then we have a straight line motion, because if this one here has the same speed as this one, this wheel does not have an engine. It's just there for stabilization, that a robot actually doesn't tilt or something like this. So if we have these two wheels and they run at equal speed, the robot just goes straight. If they run at opposite speeds, so that this one here could be 1 meter per second, and this one could be minus 1 meter per second. So the same absolute value, but different signs, then that robot would turn on the spot. And if you do different combinations, say one wheel runs faster than the other one, then this leads to motion in a circular arc. And this is something we can see here very well. So we have our robot here, and it has two wheels. And we will introduce a couple of variables now. We have a variable W, which is the width between two wheels. And if these two wheels have the same speed, the robot just keeps moving straight. But now, if one wheel is faster than the other one, we will have such a circular arc movement. So the robot drives in this circle. And we need a couple of more parameters for this. We will have this circle, and when this robot moves along the circle, we have a delta theta as the angle of how the robot is moving, and we also need a radius of the circle. So we just assume the speed stays constant, so one is faster than the other one, and the robot keeps moving, but then we don't change the speeds anymore. And then it drives the circular arc, and we have a radius for this. And I'll switch now back to the iPad to develop this with you. We will look at how we can describe the motion of the robot. So we want to find the radius of a curved path. So we want to find the radius of this curved path, and we consider a period of motion. So period of motion, which we call delta t. And the robot moves along a circular arc through an angle delta theta. And then we can think about the two different wheels. We can think about the left wheel. The distance moved is, so distance moved is VL times delta t. So VL is the velocity of the left wheel. And the radius, because we've seen before this figure in the previous slide, so the radius of the left wheel, so radius of arc is R minus half of the width. That's what we visualized before. I'll just put a quick reminder here. I'll try to visualize this down here for a moment. So we had a visualization like this before. We said this is our arc. We had the two wheels. This is our robot, should be a circle. I'll just keep it simple. And we said the distance between the two wheels is our width. And we said this here is the radius. So the radius of the arc, maybe I should write the radius of the arc is this one here. We would have a radius, something like this one here. this would be for the left wheel. So we have R, which is here, minus half of the width. And if we do the same for the right wheel, then the distance moved is VR times delta t, and the radius of the arc is R plus half of the width. And that would be just the one for down here, where we have the R plus half of the width, because this is the whole width, the distance between the two wheels. Now, because both wheels are subject to the same angle, and the angle here is delta theta, it's the same angle for both wheels, we can come up with the following one. So we can say, as a consequence of this, so we say, because both wheels subtend the same angle, we can say this angle, the change of or delta theta would be VL times delta t divided by R minus half the width is the same as VR times delta t, which is divided by R plus half the width. And then this is just simple maths. You would see that half the width times VL plus VR is the same as R times VR minus VL. Feel free to rearrange the terms to see this. And there are some interesting consequences from this if you just solve for R. So R would be the width times VL plus VR divided by 2 times VR minus VL. And maybe just to sort VR and VL correct, that it just looks better, because this is just a sum up here. So we can also say that this is VR plus VL. So the width times the sum divided by 2 times the difference. This is how we can infer the radius. And we can also infer the change of theta, so the angle, as VR minus VL times delta t divided by the width. These are just consequences from the terms above. Oh, and I saw there was some questions a few minutes ago. If the width is the inner distance or outer distance or the middle, that's a good question. It's also not visualized too great in the slides, I have to admit. To me, this one here would be uh, the middle. I would put this in the middle of the wheel. So sorry, I didn't see the question before, but I would say this is the middle of the wheel. So this is now just some of the basic properties of this differential drive, which we will need from now on to move the robot. There will be a couple of more formula and equations about how the robot moves, but we will need this to also describe later the uncertainty. And uncertainty is something that we want to correct for. For the robot motion, what one option could be an open loop motor control, and there are also so-called closed loop motor controls. I quickly want to explain the difference, what this means. So this comes from control theory. You may have seen this in a lecture, or you may see this in your advanced robotics course later in your studies. So an open loop motor control would be something like this. It's concretely a single input, single output system. So I put in U, which would be a voltage, and what I would get out is Y. So I'm putting in a voltage, and what I want is a velocity. So how the robot or that the robot moves with a certain speed. And this is probably the simplest motor control possible. You put a velocity and you want a certain speed. But in reality, it doesn't work that well, and you need a closed loop motor control. Because what we actually want to put in, we want a desired output. So we say we want the robot to drive at 1 meter or 10 meters per second. But just putting a velocity on the motor doesn't necessarily give me this, because maybe the robot goes too slow. If it goes uphill, maybe there's some dirt on the road and the robot has more friction on the wheels and doesn't move that quickly. Maybe the robot drives downhill and would even be faster. So I need to correct for this, and that's what a closed loop motor control allows me to do. And for example, you can imagine this also as cruise control. When you drive your car and you put in that you want the car to drive at 160 kilometers per hour. And maybe you drive uphill and then the engine needs more power. And that's exactly what is implemented also in your car. If you use cruise control, you would also have a closed loop control, because what you're setting is a reference, the desired output, how fast you want it to drive, but there is an error. So there's an error of your desired output, your reference, and what you're currently getting from the control, so from the control unit. So there's a difference, and that difference can be calculated by you have your desired output and you have your current output, and then that difference would be put again in some way also in the closed loop motor control, so that you could, for example, speed up or slow down slowly in order to achieve your desired output. And that's what a closed loop motor control would do for you. And we also need this in our mobile robot, because just putting some voltage on the motor doesn't lead that it drives as fast as I want it to drive, but rather I want to set a reference speed, say 1 meter per second or 10 meters per second, whatever. And then I want it to speed up or slow down in order to correct for, and I want to correct for this. And I can do such a correction, for example, with a PID control. Has any of you ever seen a PID control before? Maybe thumbs up or thumbs down if this is something you have seen before. So it has nothing to do with robot vision. It's just a very general scheme from control theory. And I'll show you now how it works. So a simple controller like PID has three components. You have a proportional part, an integral part, and a differential part. And you can take all three components, but you can also leave, say, one component out. You could have just a proportional integral control, then it's a PI control. You could also leave just a PD controller, would be a proportional differential controller. And when we see this here, we calculate an error, which is the difference between our desired output of the system and the current input and the current output. So there's a difference, and that error would somehow go into our PID controller. So this is E of t. the current error we have. And this is, so, and what we get out from this unit C here is the correction. And that would be in our closed loop motor control, for example, a voltage that would go into our controller from before, which was the open loop motor control, because we put in a voltage and this unit C gives me the right voltage so that I get eventually the desired output from the open loop motor control because I have an error here. This does not happen immediately because maybe the motor needs to accelerate for a while or slow down. So this is it's a control loop, and that's why we have also our time step t. I want to know what's u of t, and obviously I need to reflect this error because I have a difference between what I want to achieve and where I'm right now. So the difference is the current error is the one I need to put in. Typically, I cannot just use that error and say, well, the error is what I need for the output. Because what can happen is that maybe it could happen that you correct very, very quickly, say in one case, and then you put, say, a huge voltage on your open loop control, and then you actually accelerate too much, and then you're too fast. And then you have a difference again, and you need to reduce it again. And this would often lead to some kind of oscillation behavior that doesn't look great at all. So we say we have our error, but we don't take that error into account as such, but rather we multiply it with some constant. Kp. We will later see how we can set these constants, but I don't just want to take that error as such because then probably it will overshoot, then I'm too fast, then I want to go down, and then I have this massively oscillating behavior. That's the proportional part. And there's also an integral part, and the integral part means this is an integral, but the way you can imagine it in this case is actually just a sum if you see it from a computer science perspective, because in computer science we always think in time steps. So you could also see this as a sum of past errors. So in order to smoothen this a little bit, you would sum up your previous errors. You could take all the past errors and sum them up from t0 up to our current t, but maybe there are lots of old errors that are not relevant. And then this integral would also not be bounded, or it would not be fixed because you're starting with t0 and t keeps growing. So the longer this runs, calculating this integral or the sum would become slower and slower. So you could maybe say, I want to look at the last 50 errors, for example. And I sum these errors up, or if I see it from a continuous perspective, it's an integral. And then I multiply this also again with some constant. So it takes past errors into account in order to smoothen this a little bit. But then you can still improve it a little bit more because we said we have our current error, and now we've looked into all the past errors, but maybe we want to know how has the error just changed compared to the previous time step. So what I want to know is the change of the error. So this is just the derivative or the change of the error, so d of e divided along dt, along t, and that change would also be reflected with a certain constant, which is the differential gain. And that's why we sum up these three products, and what we get is our proportional integral differential control. What we need to do is we need to tune these parameters well and maybe think about of how many past errors we include. The first time I came across this was so I learned this stuff in my undergrad when I had a class in industrial automation and this kind of stuff was taught. but I needed it later in my bachelor's when I worked with drones. It was not a vision drone. The drone was rather a drone that had, or it had cameras, but we didn't really use the camera for that use case. What we wanted to do is we wanted to um, stabilize the drone. So when you have a drone and you can measure the distance to the floor with a sensor, and you let the drone fly up, but say you want it to fly to exactly 3 meters. And if the drone flies very fast, it will not stop at 3 meters, but rather you will have some momentum left, and the drone will overshoot to maybe 3.5 or 4 meters. And then a consequence could be it could bump into your ceiling, for example. So you don't want to overshoot that much. And when you go down, you also don't want to move down. You want to move down quickly, but you want to stop before the drone hits the floor. And this is the kind of stuff you can do with a closed loop motor control, like a PID controller. So you would look at your current error, say your drone is at 2 meters, but you want it to be at 3 meters, so it needs to go up. And obviously, you need to look into your error, but you don't just want to put here a factor of 100 because it will massively overshoot. It would even overshoot if this constant was just 1. But rather, you want to look at your previous errors, somehow reflect them, and maybe see some pattern in how the error keeps changing, because the closer you get to your desired height, which is 3 meters, you want to stop slowly there. And this is what will help you, what the change of error, so the differential part, will also do for you. And that's the idea of a PID control. And with this, we were able to reach very quickly our height that we desired with the drone, but we didn't overshoot much, but rather we didn't want this massively oscillating behavior, but rather smooth, move fast, but also slow down in time in order to achieve the desired speed. Maybe just signal to me if this is something you understood as a use case for which the PID control could be helpful. So looks clear. And the PID control can also be used for our motor control because we want to speed up the wheels, but also we don't want to accelerate too much and overshoot, but rather get there quickly, but also reduce the acceleration when needed. And this is something that the PID control can do for us. There are also some heuristic rules of how we can tune these parameters. So we have these three parameters, KP, KI, and KD. And there are lots of rules, and there are lots of different advice of how you can tune your parameters. Something that is often advised as an initial heuristic rule is you set Ki and Kd to 0. You increase Kd until the system starts oscillating. Oscillating behavior is not good with a certain period Pu. And this would be, we will keep this now as this gain as a Ku, another parameter. So just where the system starts to oscillate. And then Kp would be 0.6 times Ku. Ki would be 2 times Kp divided by the period Pu of the oscillation. And Kd would be Kp times Pu divided by 8. So this is a heuristic tuning rule that is overall, I think, at least a good start and easy to implement. And this PID control is also needed in our mobile robot because you later want to set when you use your wheels through your code. You want to set maybe let us drive at 3 meters per second or 1 meter per second, whatever. But you don't want to bother too much about how to access these motors in detail. So what you need is actually some more high-level library that would just allow you to access the wheels with a certain speed. And internally, you would need the library that would put the proper voltage on it, make sure it accelerates, but also reduces the acceleration once you get closer. This would be done internally with a PID control. Um, when you start building your own robot, and maybe you notice, and it could also happen when you work in this lab on your robots, you will notice you have two motors. You will have one for the one wheel and one for the other. This does not necessarily drive straight if you put the same voltage on the two motors. In an ideal world, these two motors would behave exactly the same, but in reality, they don't because the robots are always, the motors are slightly different. So when you notice this, that your robot doesn't drive straight, even though you put the same voltage on both motors, what you need to do is a calibration. And then you would have a PID control that you would calibrate, and the PID control would make sure that your two wheels actually would behave similarly, not because you put the same voltage, but you put the PID control, make sure they actually achieve the same speed. This is something that I've done a few times on my own. Maybe it's something you also need to explore in a lab if you notice that your robot doesn't drive straight. But there are lots of other reasons why your robot may not drive straight. Maybe one of the wheels is not mounted on properly. So check this kind of stuff that also the wheels are mounted properly. Otherwise, you you just do lots of unnecessary work with a PID controller here. Better make sure the wheels are mounted correctly. Now we've looked into this very low-level motion stuff. We've seen the PID control for the motor before. We've seen this circular movement. And we will now become step by step a little bit more abstract when it comes to these movements. And for this, I'm switching back to my whiteboard. So, we will now describe the motion and the state in a 2D plane. We will now, we don't want our robot to actually move such a circular movement because all of this becomes quite difficult. Rather, what we later want in our robot, so the motion and state, what we later want to do is we want to have the robot is in our XY coordinate and has a certain angle. So the angle here would be theta, which would be just 0. We could change the angle, for example, to here, and then the robot would move to here. And then we could let the robot move up here and then down here, something like this. Such calculations are much easier if we always change the angle and then let the robot drive straight rather than planning for some circular movement and how the robot should move circularly. Rather, we always want that robot ideally just to move straight to a certain point, turn, and then drive straight somewhere else again. And we need to be able to describe this state, and this state will be now described by a bold X because it's a vector. And what the robot has are three parameters, the X, Y coordinate and the theta. So X and Y define where the robot is in our world, in the XY grid, and theta is the angle. And just to use the correct notation from before, we could also sometimes say the x-axis is called, now we'll just keep it like this for now. So we have an x and a y coordinate and our angle. The angle, just to remember you, would be this one here, up here. The angle would be this one, and we don't call it alpha, we call it theta. And then we have this other angle here and so forth. So these are the angles. And initially, when that robot starts, so we start with x is equal to y is equal to theta, which is 0. So initially, all of this starts here with an angle here, which is 0. And then we can let this robot move around, and we also would require something like this. It's a very important constraint. How does our theta change? And what we typically require is that theta is less than or equal to pi and greater than minus pi. So because 360 degrees is 2 pi, and our theta would be less than or equal to pi, which is 180 degrees. So 180 degrees up here. But if we rotate too much, like up to here, then we're at 180 degrees. And then if we rotate to here, then this would not be 270 degrees, but we would rather say minus 90 degrees. So minus pi half would be here. So that's why once we are here, we're at pi, and because pi is 180 degrees, and then as of here, we would have negative values between minus pi and 0. So this is an important convention that we are using, and something you need to pay attention when you start implementing this code and you start rotating the robot. Make always sure that you have valid angles, because if you rotate your robot, I don't know, three times 360 degrees, you still always want to have an angle that is in this interval and not like, plus 5 pi or something like this. So always make sure you keep valid angles when you rotate the robot. And we can now think a little bit about how we can do a motion of a straight line. So it's just the one I had shown here before. I'll write it again in a little bit bigger, X and Y. And we have our robot that is somewhere here, and we want to move it to up here in a straight line. And we can wonder now, how can we actually express this? So we have the angle, which is theta, and I have some xy coordinate here, and I have an x nu and a y nu. And this update can be expressed the following. I can say my x nu, y nu, and theta nu is, I have my old x and I add something on top. I have the old y and I add something on top, but my theta does not change, because all I'm doing is I'm moving by a straight line, but I'm not changing theta. So theta stays. And now this is just simple geometry. So we have a distance here. This is a distance d that we are moving. So we say this is x plus d times cosine of theta, and y is d times sine of theta. Just simple geometry of how we update x and y. This is a straight movement, so I'm writing this here, straight line. This is one movement, but we could have a different movement as well, in which we're not moving straight, but rather the robot is rotating. So we are updating its state by doing a rotation. And this can also be expressed as x nu, y nu, and theta nu. So x and y stay, and our theta we can express as the theta nu is theta plus alpha. So this up here would be the theta, and this would be alpha. So we say theta plus alpha, and that's the update. I'll just switch back to the slides. We've seen what our state looks like, and we've seen that our theta needs to be within minus pi to pi. And we've seen how we can do these updates when we move straight or turn. There is obviously you can do the movement along a circle. So if you are in this location and you want to drive to here, you can either move straight, but you can also use your differential drive. So you don't need to turn explicitly and then drive straight, but rather drive from your location to up to here, using this differential drive by using different velocities. And then you could have this circular drive. You can update X, Y, and theta by using some of the geometry we had before, where we said our delta theta is the angle that we are turning, and we want to plug this in, and you can derive something like this. It's a little bit more geometry, but I'm not discussing these equations here in detail. But in case you want to implement such a circular movement, you can do it this way, and this R would be the one of your circle. And we've also seen how we can infer R from the different velocities before a few slides ago. And what we are doing is position-based planning. I've told you about this before, position-based path planning. We move from one point to another, and in each point, we would just turn adequately so we can change our angle to drive from one location to the other one, and we would then turn the robot and then move straight. And this can also be expressed with our equations. So our robot is currently, imagine our robot is rotated correctly now. So it's just pointing where I want to drive. And I am at a certain coordinate x, y, and I don't need to rotate the robot anymore. Then I need to wonder, how much do I need to move along x and how much do I need to move along y in my coordinate system? And I want to drive to a waypoint wx, wy. And for this, I would just say I need wx minus x, my current x, and wy minus y. And then I have that changes along dx and dy. But I think I can also visualize this briefly just to make sure we are all on the same page. So we will do the position-based path planning. So we said we have our dx and dy. So what's the difference in x and y? This was wx minus x and wy minus y. Because we were, so say currently at x, y, theta. We want to go to wx wy. But now we have the difference along x and y. I need to charge the iPad now. And do you know how we can calculate the distance? So I'll show you where we are. We are at X and Y, and I'm here, and I want to drive to there. So I have my dx, which is here, and my dy. So how do I calculate my distance that I actually need to drive with the robot? Let me know in the chat. It's just basic geometry, just a quick revision of how I can calculate this. So D is, or maybe turn on your mic in case you want to tell us. Well, I see a green reaction, so someone knows it. It's actually fairly easy. It's just simple geometry. Oh, um, we got something in. So what you wrote us in the chat is something slightly different because we said how we can provide it from before, where we said we have an angle and and that's correct because we want to get from here to there. And we wrote before of how we update this one here. But I want to know now how long I need to drive or what's my difference. So not how to update the state, but how to calculate how long or how far I need to drive. We got the right one now in the chat. It's dx squared plus dy squared, and then we take the square root of that. So it's just simple geometry. And then I have this distance that I need to drive, and then I need to stop here. But I have one more problem. I need to make sure that first I need to rotate the robot. Imagine I was here looking in this direction and I was in this point X, Y, and I looked into this direction, the red one, so I also need to rotate. And now, so I first rotate and then I drive. And how do I calculate this angle? So I need, because we've said before, we call this alpha, the update of the angle. And so how much I need to change the angle. And it turns out you can calculate this alpha with the tan minus 1 function of dy and dx, the fraction of dy and dx. This works theoretically, but in practice, this will not fully work because we always assumed that our angle fulfills this constraint. And the tan minus 1 will not return us the correct angle. So it also depends on where I am in the grid, in which of the quadrants. So I can use the tan minus 1, but I may need to correct for what's coming out from there, depending also on the quadrant. So what is better is it's the a tan 2 function where we pass dy and dx. I've mentioned the a tan 2 function, I think already in the second lecture briefly, and suggested you to take a look at it when we looked at one of the edge detectors, where we also calculated some angle of how the intensity changes in which direction. And the a tan 2 function is something that is implemented in a lot of math libraries, so it's also available in the Python math library to you. And this one here will be actually much more helpful, so we don't need to look at these special cases like with the tan minus 1. It's the a tan 2 function, And important, I don't pass a fraction, but rather the two parameters. And from that, the a tan 2 function gives me the correct angles. And the robot must rotate then. And when your robot rotates, just make sure that it also rotates in the right direction. For example, you could have something like the following situation. So we have XY, we have a robot that is here and it's looking in this direction and it should drive down here. But we always rotate anti-clockwise. So what I actually want something like this. And then the robot would rotate by this, like maybe like 300 degrees, which is not very smart. So in such cases, please don't always rotate your robot overly long anti-clockwise, but rotate it in the opposite direction, which is much faster. So it's faster and needs less electricity. So this is something very important. So the angle by which you're rotating would be would be beta. It's our alpha from before, but you would subtract your current theta, your current orientation, and this allows us to move the robot as efficiently as possible. But when you shift by this angle, always make sure that your beta is less than or equal to pi and greater than minus pi. And you can add or subtract 2 pi from the beta so that it falls into here. And all of this helps you to assure that you're turning, if needed, in the opposite direction for a few degrees rather than doing a big turn. Maybe just confirm with a reaction that you got this, because we want to make sure that you don't rotate overly much, which needs a lot of electricity and also slower and adds uncertainty. Then, this is what I had just shown you. Now we've done movements. They are uncertain, but this is something we will look at next. But first, we study some sensors. So our mobile robots also have sensors. And the sensors allow us to gather measurements or readings. And there are actually two types of sensors. Most sensors that you're looking at are outward-looking sensors, but there is a smaller class of sensors that are called proprioceptive sensors. So what are proprioceptive sensors? This means self-sensing. So these are sensors not giving us external information, but these are, for example, only sensors of our internal state and motion. Without measuring the environment, but maybe the current motion of our sense of our robot, or maybe the heat of the robot, or something like this. And the value of such a measurement, ZP, will only depend on the robot. So ZP is the measurement, and it only depends on the robot, and it's a function of the robot, which is X, our robot state, and it's not reflecting any of the outside environment. While most of the sensors we need, in fact, will be from the outside environment, because the outward-looking sensors depend on both the robot state as well as the environment, our world around it, which we call Y. And there are lots of outward-looking sensors we deal with. For example, we may wish to localize with respect to a certain map. So we know a certain map and we want to know where are we in the map, so we need outward-looking sensors. We may wish to recognize certain places and objects. Maybe we want to figure out free space and avoid obstacles. We want to interact with objects and people. We want to be aware of our environment. So for all of this, we need outward-looking sensors. And there are, so these are some Lego sensors, but as I told you, the Lego Mindstorms, it's quite helpful and you can connect it with a Raspberry Pi or some other platform. So you don't need the Lego software, but the hardware is actually quite helpful and doesn't break that easy. But there are obviously other vendors too. And for example, a touch sensor would be on off and you would either touch something or not touch something. So it could help you to maybe detect collisions early and then stop without driving. A very simple sensor. And there could also be some strategies after a collision. So we don't have cameras right now. We have a very simple robot with very simple sensors. And we are colliding. So one strategy could be maybe you're reversing, exploring, going around something. If it's a very lightweight object, maybe in a certain use case, you can just move the object if you wish. Um, Maybe not for an autonomous car. Maybe you don't want to move pedestrians and other cars. But if it's a cleaning robot and there's just a toy on the floor, maybe you can just move it. If it's a wall, you don't want to keep bumping into the wall, then it's a different thing. Then there are light sensors. Light sensors detect intensity of light from a single forward direction. And if you have multiple of these light sensors that point in different directions, maybe this can help you to guide steering behaviors. There are also sonars. Sonars, they help us they give us depth, so they give us distance to something. We don't know what's in front of us, could be a wall or an object, but these sonar sensors, they give us distance. They are very helpful, but they come with very noisy measurements because this stuff here, like a touch sensor, this is not noisy. It's either on or off. But say a sonar is typically very noisy, so you don't always get reliable values, but maybe you get values that are just wrong because of some sensor issue, whatever, temporarily. So this will lead to uncertainty that we need to handle because maybe we're 1 meter away from a wall, and maybe for the tenth of a second we get a different value that we are 5 meters away. And then we get new measurements, and we somehow need to plug in these new measurements and make sure that we don't get disturbed by all this noise. Um, these sonar sensors are helpful. For example, also underwater, where vision or other sensors could be very difficult. And sonars work for underwater robots also extremely well. And in this course, we have a computer vision course. So a different outward looking sensor is a camera. And this is the one we have in our robots. So you've picked robots from the deep learning lab. Make sure you only have robots that have a camera. If you work with a robot that has no camera, it wouldn't be probably really a vision project unless you have a LiDAR or something like this. But when you pick a robot and you want to do a robot project, make sure it's a robot vision project because it's a computer vision course. And with cameras, we can understand our environment very well, and what we get are images. It's an image sequence. But a single camera only measures, or it only gives us pixels, but a single camera gives us no depth information. So the sonar gives us a depth information. It doesn't see anything else, but it tells us how far away we are from something without knowing what that something is. But with a camera, we can see things, but we don't understand the distance. Because just from a single camera, distance measurement does not work unless you use some sophisticated neural networks, but that's something we see later in the advanced topics. So what you could have is either you use some very complex neural network approach to estimate depth, but you could also add a second camera. Sometimes we have students, they add more hardware to these robots, mount on more cameras or more sensors. So all of that is possible. And cameras are very interesting in a robot vision, in a robot project, because we can do robot vision. We can recognize objects, we can do location recognition, We can do tracking. Um, we can do 3D reconstruction. There's a huge link to biology because we as humans, we have eyes. We have two eyes, which is a huge advantage. And nowadays, cameras for mobile robots have become general purpose, low cost. But when you want to process the image sequences, this is computationally expensive. So we have these Jetson GPUs. On those, you will not be able to run a super big neural network efficiently. Maybe a smaller neural network at a few frames per second. So there are also lots of other pre-trained neural networks and models that you could run on that Jetson GPU, but maybe not a super huge neural network, but more a compact one. But we looked at YOLO last week, no, 2 weeks ago. We looked at YOLO as one very famous pre-trained general purpose vision model. You can use that one also as a mobile version. So there are smaller versions that you could run maybe on your phone or on this robot or whatever, but maybe not the big YOLO as such. So that's something you need to pay attention to. And we not only have these Jetsons that or chatbot platforms bought a few years ago, there are also newer ones in the deep learning lab, but still these edge GPUs, they are limited. They're not as powerful as a GPU in at home if you have a big gaming machine or whatever. So pay attention to this. And obviously, if you use that GPU a lot, your battery will also decline. So this is something you need to bear in mind. Now we have done simple motion and we have done sensors. And we will now look at probabilistic robotics. What is probabilistic robotics? Our robots, they deal with uncertainty, or they need to deal with uncertainty, because the real world is messy. In the real world, motions and measurements are uncertain. I want a robot to move 3 meters, but it will not move precisely 3 meters. I want it to turn by an angle. It doesn't turn exactly by that angle. So there is uncertainty in the movements, but also in the measurements. We've seen this with the sonar, and so with a camera, because the camera will deliver noise too. So we need to reflect this uncertainty in our models. And for this, I will switch back to the iPad again. So now after the break, uh, we will see how we can actually express uncertainty with our framework we had so far, because the robots don't move as we expect in reality, because we've said before we have our x nu, y nu, and theta nu. And we said if we want to move straight, we said before, theta would just stay as is. But if I move perfectly straight, the angle will stay, but with uncertainty, because the wheels, both wheels will never drive exactly the same. Somehow the angle will change at least a little bit by F. So F is the uncertainty if I want to move straight. We've said X and Y get updated. So we said we would have D times the cosine of theta, and here the sine of theta. But in fact, this also becomes a little bit more complex because the robot will not move precisely by distance d, but in x maybe d plus e, so e could be plus minus negative, and in y as well. So the robot will not move exactly the distance, but rather a little bit more or less because of the uncertainty. And this was for the straight line movement, but we've also said if we rotate the robot, x and y nu and theta nu, um, then we are also maybe not just perfectly rotating along theta, we said theta plus our alpha. This would be the rotation because we rotate by alpha, but there could be some small uncertainty chi as well that I'm rotating more or less by a few angles. So these are these update equations from before. They were for totally certain movements, but we're in a real world that is messy. So we have some uncertainty we need to plug in here as well. I'll show you now what this looks when you try to visualize it. These are our equations from just now, and we can try to visualize this. So we have these noise terms, which are E, F, and G, and we could have a robot that starts down here at 0, 0. And the robot is tasked to move, say, 10 meters, or could be 10 times 10 centimeters, could be 1 meter, whatever. It moves by a certain distance, moves more, moves more, and moves more. And sometimes the robot may end up a little bit up or down, not always perfectly straight, and not the perfect distance that I want, but rather moves a little bit further or a little bit behind. And this can be here visualized not just for one robot, but for many robots. And we see we spread out, the more these robots move, we spread out. Then, after 4 steps, we rotate the robot by 90 degrees and move it out. And we see we again have more and more noise because we are always adding uncertainty. We don't have any like correction for the uncertainty, but a robot that was here, say, spread out a bit up, gets turned to here, and then gets spread out more when the robot drives straight. And then up here, I rotate again, and it spreads out more. So the more I move and the more I turn, I get more and more uncertainty. And we see all of this spreads out. So later we need to correct for the uncertainty, but this is something we will see. But say this is maybe an okay calibrated robot. Now we can have a very poorly calibrated robot that would look something like this. So already starts to spread out a lot. And once I start turning, it spreads out. And eventually this is all spread out here. And we really don't see anything useful anymore. So this is something I generated a few years ago with, I don't know, matplotlib. So with matplotlib, you can generate such interesting plots as well. And we see this robot is maybe okay calibrated, could be calibrated better, but perfect calibration doesn't exist. So we also need to correct for this kind of stuff. When you want a well-calibrated robot, so in average, this should return the desired location, but it will still scatter out to some extent. And we want to remove systematic errors. For example, a systematic error would mean that these errors don't have zero mean. That would be a systematic error. For example, if like one wheel is really lagging compared to the other one, then these errors would always be biased in some direction and you wouldn't get a zero mean error. So that would be a systematic error that you would need to fix. Now, in order to handle this uncertainty, we need statistics, in particular the Gaussian, so the normal distribution. That's quite a helpful approach for us to model the uncertainty and later to correct for it. So we will have uncertainty in the sensors, we will have uncertainties in our sensors, and we can, for the sensors, we can describe this with a Gaussian. We can say that we have a probability distribution of the measurement given our coordinates x and y. And you can, for example, for this we need a likelihood function, and this likelihood function allows us to describe the sensor's performance. And this likelihood function, P of set given V, is a function of both the measurement variable set and the ground truth V. So the ground truth would be correct value, but we have the measurement set. And this can also be plotted. For example, here, the first plot would show constant uncertainty, that the uncertainty is constant. We could also have uncertainty growing. So the more you keep measuring, the more uncertainty you get. But you could also have a systematic bias. I've mentioned the systematic bias before when, for example, say your wheel is lagging in the movement, in the measurement, maybe your sensor has a problem, or maybe your distance sensor is not perfectly straight on the robot, but moved by a certain amount of degrees, then you would have a systematic error, a biased sensor. And I will skip a few of the slides and rather explain this orally when we now look at probabilistic localization. So localization is one of a few very important tasks in mobile robots, because they need to know where they are actually on the map. In an ideal setting, you know the map. We later look at how we can learn a map, but you know your map and you want to know where are you on the map. And we have a robot, for example, that is currently here with a certain angle. And what this robot has is a device to measure its depth, so the distance to the wall, to the next object or the wall. Just measure the distance. It could be a sonar. The sonar doesn't see it, only knows distance to something that is in front of us. But we could also have two cameras, so a stereo vision approach, or we have one camera and use some depth estimation with some advanced neural network. So we would measure distance. And this is what we can do. And if our robot is really here, then we would measure the distance and get the correct distance if there was no uncertainty or anything wrong. But in reality, it doesn't work this way, because the robot thinks it's in a certain location. So the robot thinks it's here because it moved from 0 up to here, but there was uncertainty in the movement. And maybe the robot is here with a different angle. And the robot is maybe looking up here towards E and not towards C. So the robot, what it actually wants to do is it wants to know better where it's located. What we have is what the robot believes where it is, but we also have sensor updates from the sonar or the camera, whatever. So, and we want to get then something, or we want to do something that's called probabilistic localization. So we want the robot to be that it knows where it is located. This is overall challenging because every robot action is uncertain. Every movement is uncertain. Every sensor measurement is uncertain. Every state estimation is uncertain, because we want to estimate the state. So in fact, what we are doing now is filtering. It's a term you remember from last week when we looked at image sequences and temporal models. We saw Kalman filters, or filters in general, that do state estimation. And now we are doing state estimation in a robot, that the robot estimates its location based from what it knows, but also what it measures. But all the actions are uncertain, the sensor measurements are uncertain, and the state estimation is uncertain. And we want to build a probabilistic inference to do this. So what we need is Bayes' rule. We've seen Bayes' rule last week, and you're all familiar with it. And with Bayes' rule, we're actually able to build our particle filter, because with Bayes' rule, we have our current state estimate. We're doing actions, and actions add uncertainty. But then we're doing measurements, and measurements allow us to get new information from the outside world, which are again uncertain. But with Bayes' rule, we can incrementally put that information from the sensors into our robot state in order to estimate it. There is a few slides with extra text for revision or whatever, but I'll just explain you this step by step what we are doing. And you can revise these slides later in case you want to do some further readings. But I'll show you step by step how this particle filter is working. And we use the Gaussian distribution to model the uncertainty for the sensor measurement, because not every sensor measurement is probable. Maybe there's suddenly just some very unexpected value coming from the sonar. It's still a measurement, but uncertain, but it's very unlikely. So a Gaussian distribution helps us to reflect if that's likely or not, and how much we can plug it in when we do our state estimation. And particle filters help us to do this. Particle filters can be used for localization, but they can also be used for other state estimation problems. And what we have is a cloud of so-called weighted particles. So in the particle filter, we not just have one location of the robot, but lots of possible locations, each with a certain certainty. So it's weighted. And each of these particles refers to one possible instance of our robot. And we have weights of how likely these locations actually are. And what we are doing is we're doing motions, and motions are uncertainty. We plug that uncertainty in the update of our particles, and then we do measurements like a distance measurement. And then we get these distance measurements, and then we try to plug that information into these particles and then see which particles most likely would match with their location as well as a distance that we got. And it's very important, a distance, because it's not necessarily this wall over here. Maybe some particles are rotated and they would look rather at this, or they are shifted up here and they would look up there. So we try to plug in this measurement information and then see which particles are most likely where the robot actually could be. And then we do a sampling procedure that we actually get rid of the unlikely particles and keep the most likely ones, and we replicate them. So we do a normalizing and resampling strategy. So weak particles disappear, likely ones continue to exist or get reproduced. And then we have a better estimate of where we are. Then we do movements again, which add uncertainty. Then we add measurements and so forth. And for this, there's a very good video in YouTube. For copyright reasons, I'm unable to record this here, so you would just open the YouTube video on your own, and I'm terminating I'm stopping the recording very briefly once I have changed the screen share to the YouTube video, because this could possibly lead to copyright issues. So I'm pausing the recording. Please watch this video on your own, and it comes with a great explanation. And just made a mistake with the screen share, by the way, because I need to screen share the browser. And this video here explains the particle filter, but recording is stopping quickly. Now, we've discussed the YouTube video, so welcome back to the recording, but feel free to watch it on your own. And what we need in this particle filter is a particle distribution. We need a certain number of point estimates. So not just one point, but xi. And these are just the ones we've seen before, the xy coordinate and the angle of the robot. Then our full particle set is a set of these pairs of a particle and its weight, because we said some particles are more likely than others. And we could start with maybe 100 particles. In the video you saw it was far more than 100, but let's say we have 100 particles now. All the weights need to add up to 1. So this is a constraint that we got. and later these weights don't add up to one anymore, then we need to do a normalization. What we saw in, well, we start with this. What we saw in the video is a global localization. So the robot was put somewhere in a known environment, but the robot did not know at all where it is initially. We didn't tell the robot. We just put it some in a map that it knows, but it knew nothing. So these particles were very well spread out. And as the robot moved around, also the particles got updated, but then the measurements were done. And then over time, a lot of particle clouds started to die out because they didn't at all match these measurements. And that robot in the video had not just one distance sensor, but multiple around it. And this is global localization. So you put the robot somewhere in the map and it needs to figure out where it is by doing movements and measurements. So initially, these points, these particles, they would just randomly be spread out in the map, and all the weights would be the same initially. When you start with in a given location, so the robot knows in which location it starts, then we would have a continuous localization, and the robot would keep moving, which adds uncertainty because actions add uncertainty. But initially, all these 100 particles would be at the same location with the same properties. Also, each would have the same weight. But then these actions are being applied to these particles, and some particles will move more than others and reflect the noise a little bit more or less. And then we do the measurements, and then some particles may die out quickly, others are becoming more likely, and we're doing this normalization, and based after the normalization, we do a resampling. So two differences, continuous localization and global localization, and the video showed us global localization. And if I want to infer from this cloud of particles where my robot would be in average, what I'm doing is I have each particle, which has a certain state, and they're all slightly different because I have uncertainty, but some are more likely than others. So each state has a weight, and I'm multiplying the weight with the state, and I'm summing this together. So I have a weighted average, and that weighted average, that would be the location in which my robot most likely is from the particles. And the steps in the particle filter is what we have seen before. We are doing the motion, and we're doing a motion as a robot move 3 meters. And we are doing the motion, but we are also doing the motion, we're applying this to the particles with our noise. So some particles will move more than others, some will shift a little bit, some less. Then we do the measurement update based on our sensors, for example, a sonar. And then we are doing the normalization after this. So we're doing the measurement, and we are applying these measurements to our particles. So we would see how likely some particles are and not based on where that particle would be and the measurement update. So we plug the measurement into these particles, and for this we need Bayes rule. Then we do the normalization, and then some, because these weights, they don't add up to one anymore. So this would be then the normalization. And from the normalized weights, we do a resampling. So very unlikely weights, very unlikely particles will disappear while the likely ones get replicated. And then we keep doing the next iteration. This we've seen before, this figure, which was for the uncertainty in the movements. And it's just to show you here again, as we move, we become less and less certain. And if we measure distances around us, and we would measure based a distance on a wall or maybe some other object that could be in this map, maybe we're driving around some different objects, and we do measurements, maybe not just straight, but measurements into various directions, then our particles would actually get updated with the measurement update, and some would disappear, and the most likely ones would stay. And this can be done fairly easily with Bayes' rule because we're taking our old weight, we have the likelihood of the measurement, um, so the likelihood of the measurement given where our state would be, and this is the new weight. This is just a numerator from Bayes' rule. And we don't have the denominator. So the denominator is something we can explicitly add, or we just do the normalization later to get proper probabilities of these weights. And the normalization is again fairly easy. Each weight will just be divided by the sum of all the weights, and then I got my normalized weights. And from there, I'm doing resampling. There are lots of resampling strategies available in libraries. For example, a resampling wheel is typically a strategy that could be used, or other sampling techniques. For example, working with the cumulative probability distribution and picking from there by generating random numbers and then picking the particles whose cumulative probability is intersected there. But you can implement resampling on your own or use a library. There are lots of resampling libraries and strategies available, and all you need are these weights. So it's totally, the resampling is totally independent of the measurements or how the measurements work. You do the measurements, you do the measurement updates, and from these weights, you can resample. So you can nearly use any resampling library that you wish for this kind of stuff. So this is the particle filter. Every year, some students implement a particle filter because, yes, you could use a sonar, but you could also use a camera for depth estimation, or maybe localization is part of a bigger project with the robots. So some students may add a sonar or a LiDAR on top, and then the robot can locate or can find its location and then do something else with the camera. So there's lots of freedom. What would not work is a pure sonar project because a sonar has nothing to do with vision, but you would either need to use this as part of the project and do something else with the cameras, or you would use your cameras, maybe two cameras or one camera with some other tricks to estimate the depth. Now, we've always assumed that we have a map available. That's not always the case, and that's why there is also simultaneous localization and mapping, SLAM. And with SLAM, your robot becomes truly autonomous because the robot does not know its map, so it can hardly locate itself in the map, but it's trying to learn the map based from sensors, and it's learning the map, and then it's also determining where it is in the map actually. SLAM is something that became popular around, say, the late or sometime in the 90s. And there's been huge progress in the 90s with SLAM, and now obviously ever since. And I don't know if you have a cleaning robot and you put it in your kitchen, the robot obviously doesn't know your map, but it's learning the map while locating where it is. And there's again a YouTube video that explain or visualizes SLAM quite well. You can also switch to that video. So, we've looked at SLAM, and there are a couple of advanced topics I want to at least briefly mention. This is an introduction to computer vision, and we've already done more than you would see in a lot of other computer vision courses. And given the lectures are only the first half or first 40% of the term, we've done lots of content because we've looked at how we can represent pixels and filters, how we can work on regions of images, how we can detect features, how we can recognize objects and use convolutional neural networks for this as one solution. We've seen image sequences, including the Kalman filter, which you can apply to lots of different problems, as well as the particle filter. They make different assumptions and have different use cases, but the particle filter is certainly easier to understand than the Kalman filter, but it's made for a different class of problems. We've seen now mobile robotics for those who wish to do a robot vision project. And we look at a few selected topics just to inspire you with some more topics that are important. Some students, they also pick these advanced topics and study them and work on them in their projects, which you're also most welcome to do. Some students may have done some vision before taking this course. Some are newer and may want to focus on one of the earlier topics. Do a project that is obviously sufficiently challenging, but also something that you enjoy. And if you have done lots of vision before, because we also have some master students taking this course, if they may have done some vision before, so they may pick one of the advanced topics. 3D vision is a very hot topic because with 3D vision, we actually tend to see the world as it is because our world is inherently 3D, but with our vision system, we recognize it in 2D, and with one camera, it's really in 2D, but we can get also 3D information from the 3D world. We as humans, we have two eyes, so we can get a better understanding of depth, so distances, but there are also 3D reconstructions from multiple images, maybe localization in a 3D world. Now, how do you build a 3D vision system? One approach is stereo vision. So stereo vision is having two cameras being at different locations and different angles looking at a scene. So we have a scene, we have these two spheres, and we have this camera, and it would see this sphere, and which is partially including the orange one, that is the bigger one. But we have this camera here also looking at the scene, and from that camera's perspective, on the right, there's a green sphere, and on the left, this this orange sphere. So with stereo vision, you can get 3D information from this world by using two cameras at different locations and different angles. And what you need to do is some maths, which is called epipolar geometry. Epipolar geometry allows you to calculate the depth from the information that you've got. Epipolar geometry itself could be one 3-hour lecture in this course, but it's an advanced topic. And what has become more popular in recent years is that you use neural networks. And with a neural network, what you could try is you have images and you have one camera, but you have maybe another device that can measure distance for you at the time you're taking the photo. Maybe some sonar or some other device, or you could simulate this in a scene that you have objects and distances, and you could try to train a neural network on this. So, and what a neural network would be trained on is as the input, the images, so the pixels, but for each pixel, you would also have a depth or distance information, and that would be the labels. So you not only have one label, but you have a lot of labels. You have one label per pixel, and you could build such a neural network that it learns the distance or the depth of each pixel in the image. You would need to do this on lots of images, but then the neural network can actually learn to predict depth. This is still uncertain, but it works nowadays quite well. Such neural networks are also available as pre-trained nets, if you wish, and then you can actually put in a new image and predict per pixel or per region, whatever, its depth. So this is something that is really cool. You could try to run maybe a very small neural network of that sort on that onboard GPU. Some students in the course that do a robot vision project maybe run bigger computations on their laptop, and the robots are connected through Wi-Fi. This may add some delays though. Epipolar geometry is a totally different approach, but you need two cameras And maybe it's a more lightweight approach from the computations, less complex than a neural network, but you need two cameras. So feel free to maybe investigate this. I've also published some work on 3D vision a few years ago. I wrote a book chapter on some work which was about applying machine learning to radiology. And what one challenge was, if you have like these 3D scans, say from a CT image, from a CT computed tomography process. What we used was machine learning to automatically segment certain organs from this torso, because this is the human torso, and in there are organs, and we want to segment them. And what's typically done is that doctors try to segment this, but it's a 3D image, but they work with 2D screens on that. And then it's a lot about experience and expert knowledge, whether you can segment this well. So we build a neural network that can segment organs from this torso. And we may recognize certain diseases on these organs. And then if you look at these diseases, or at the organs that are segmented on a 2D screen, it's again not great because you're looking at a 3D image on a 2D screen. So, and doctors are often not too much into computers. So they don't like this either, using a mouse or a keyboard, and you have all these hygiene issues. So this was the actual torso. And here the we have the segmented liver. And what we did is we projected it on a Microsoft HoloLens in order to visualize the segmented organ. So the computer vision part was this one, segment the liver from the torso. And then we also added this one here, computer graphics, to visualize it on a HoloLens, so doctors can now walk around the organ, they can play with, they can use their hand to rotate it, and so forth. So this is some work that we published a few years ago, and more doctors are now interested in this kind of stuff. And we were doing some of the pioneering work around this. Then one kind of neural network architecture that has also become popular in the last 5 to 10 years are generative adversarial networks. The term generative adversarial network is a bit confusing because you have actually two networks. You have a generator and a discriminator. And what you have is you have real images, and with a generator, you are creating fake images. And the discriminator shall be able to determine whether the images you're putting in this neural network. So discriminator does not mean discriminate against someone. It means to distinguish, to classify. And we can classify this either into real or fake. And the interesting thing is this is a game theoretic approach because these two neural networks are interconnected, because the discriminator tries to get better, but the generator tries to get better as the discriminator gets better and tries to generate better fakes. And the discriminator again tries to get better because the generator gets better. This is something that has become quite popular in recent years. And these GANs, these generative adversarial networks, they are oftentimes also used for such applications where you have a human photo and you can ask the neural network to make you younger or older or add glasses or change whatever property of your face. And this can be done quite well with generative adversarial networks. Generative adversarial networks are also helpful if you need to generate more training data for a more sophisticated machine learning model. So you may have a limited amount of training data, and you may need to create more training data. And for this, you can also use generative adversarial networks. Um, a lot of things, like we will soon see transformers. As you know from your classic machine learning introduction, there is supervised learning, unsupervised learning, and reinforcement learning. But there is obviously a few more extensions of this. For example, you have semi-supervised learning, which combines supervised and unsupervised learning. But there's also self-supervised learning, which is in fact the foundation for a lot of models like transformers that have become popular and that I will talk about in a moment. And with self-supervised learning, we can use a limited amount of data and try to learn patterns or sort of learn new concepts. And these concepts can be used in the training of the model then. There's a very good video um, about self-supervised learning, and this is based on a blog post that was written by, can just quickly switch to YouTube. There was a blog post from Jan LeCun and his team at Facebook AI Research, and they wrote a post about how self-supervised learning works. And someone here did a video and analyzed the blog post, provided some examples, and explained how self-supervised learning works. It's a very good video. Again, I'm not playing it here because it's 1 hour, but feel free to study it at home if you wish, because it could provide you with some valuable insights. And self-supervised learning is the foundation of transformers, and transformers are being used nowadays as vision transformers, like DALI and lots of others, where you can generate images from descriptions, from prompts, like you can generate paintings, you can generate new furniture based on requirements. So these are overall very exciting times because we can generate lots of images from prompts, and we can easily change the prompts and then regenerate. And this obviously has massive impact um, on the creative industry. You can use this for images, you can use this for text, for videos. And it's all based to a paper that goes back 8 years ago that's called Attention is All You Need, that explains, that introduces uh, the the attention mechanism and a neural network architecture. And the right end of this neural network architecture is actually the transformer architecture. And the transformer architecture is now the basis of ChatGPT, DALI, and lots of others. These kind of models are discussed in greater detail further in your studies. In the big data class, I talk a bit about them, but also in the deep learning class taught by one of my colleagues. And since this is an introductory computer vision course, and you still need to learn a bit more about machine learning and neural networks, we're unable to discuss vision transformers in detail in this introductory course. But we have very ambitious students, and if you want to pick vision transformers for your project, that's also fine. Last year we had a team. What they built was an app, like you take a photo of a dish, and then the transformer model would analyze the dish, and it would generate you a recipe. So how to cook that dish actually. This is something I found really cool as a super advanced project, but I'm not expecting you to build such advanced projects because you need to pick a project in which you can thrive, you can advance, learn new stuff, and build something useful. And some students may be more advanced than others because this course is taken by, I don't know, 250 students or something this year. And maybe 150 take this as a mandatory course in their fourth semester, and many others take this as an elective. But some students who are very ambitious may want to look at vision transformers and how to learn how these or how transformers, first of all, work. Um, this is explained well in the Bishop book that I mentioned in the literature of the course, the deep learning book from Chris Bishop and his son, that appeared 1 or 2 years ago. And that book also explains quite well how a vision transformer works. as one possible reference. Now, these vision transformers, they are helpful, but for the last few years, some rumors have been circulating that the vision transformers would totally replace the convolutional neural networks. Um, I personally don't think that the vision transformers will replace the convolutional neural networks in total. So convolutional neural networks are very helpful, obviously, for vision. They can be applied to other problems as well, even natural language processing problems. And in the field of natural language processing, we see that transformers have advanced a lot in recent years because they allow us to capture the relation between different tokens or different words in a text. And but training transformers from scratch or even running them is quite expensive. There are also small ones, obviously. Um, and in computer vision, such vision transformers, they would rather than analyzing the relation of different words, they would analyze the relationship between different portions of an image. And a vision transformer has a totally different architectural design than a CNN, a convolutional neural network. The convolutional neural network has various constraints and works very well on these 2D inputs and learns features that can be applied throughout or that can be recognized throughout the image. The uh, transformers, they try to tokenize this input. It's a totally different approach. And I think as a trend, a transformer would need more training data than a comparable convolutional neural network because the convolutional neural network has its geometric properties included in its architecture. We've seen this with the equivariance, the spatial constraints, and so forth, and parameter sharing. This is all baked into a CNN from its structure, and the transformer needs to learn such properties. Yet you could use a transformer maybe that is pre-trained. Someone else has pre-trained it, and maybe a smaller one that you can still run on your laptop or whatever. Um, the transformer is overall more flexible, and because there are no such geometrical constraints in it, and it needs to learn them, maybe the transformer could converge to even better accuracy. So you need more data, but maybe better accuracy, but training is more complex. So it's sort of a trade-off that you need to make. And I think the convolutional neural networks, they have been now well established. They've been used for the last 30 years and well improved. And there are obviously also some approaches to combine convolutional neural networks with self-supervised learning. We will see in the next few years how all of this evolves, but it's not like that the vision transformers are totally replacing CNNs. Rather, they address a different trade-off, and based on your use case, you can pick one of these two architectures or pick both and compare them. Now, we are finishing now the content of the course, and before I'm saying a few words about the projects and the organization is, you will deal with me again a few times in your studies. So many of you got to know me in the algorithms and data structures course a year ago. Now you're taking computer vision. You will see me next semester again when you do your internship. We have these two internship accompanying courses. And the internship accompanying course one is mine. It's the innovation management for AI course. This one aims to build a bridge between building prototypes and commercialization. So we look at issues that you will face when you try to commercialize AI, make money out of it, put it in a company. There are lots of new challenges like project management, regulation, expectations by stakeholders, fears. And maybe AI is not a silver bullet for a lot of problems. This is what we discuss in innovation management for AI. In the sixth semester, so in 1 year from now, I run these AI projects together with my colleagues because we are happy to have so many students. So We're not able to supervise all of them at a time. So we split the cohort of students into various subgroups. And I supervise this summer about 80 students doing the AI project, but we have two colleagues who are maybe jointly supervising another 80 students. And in my case, we do large group projects with companies. This year, we have about 7 projects working with 2 industrial partners. So you work in a big team on a big use case. Every year, we have different partners, and you will see next year what projects we have available and to which professor you get assigned. I also teach the quantum computing elective. I always teach this in the winter term, so starting this year in October. So quantum computing is probably the most popular course in a whole university, and every year the number of students kept doubling. It's it's a generic or it's an elective that is interdisciplinary for everyone at the university. All you need to know is you need to know coding a little bit at least, and you need to know linear algebra and complex numbers. If you know more about computer science, it's helpful, but it's not required. And we start with linear algebra and complex numbers. So we do linear algebra and complex numbers, and we actually build from complex linear algebra all the stuff we need to do quantum computing, which is a different computational approach. If you want to do the elective, make sure you register early once these courses become available in iLearn in August or September. But you cannot register in advance, and I'm not in charge of iLearn, so you would just need to see when you're being informed that these iLearn courses are created, because this one is capped to about 100 students, because otherwise we would have 500 students taking the course, which is great, but you need to give seminar presentations, so it's just too many seminar presentations. And since it's a pure elective, we can cap the number of students. In the 6th semester, you have this deep learning big data module. Deep learning is a submodule taught by Professor Wahl, and big data is the other submodule. I'm currently teaching it, but next year, most likely, a new colleague will teach big data because I have too many courses. So we've hired a new professor. She's starting this year in October, and she's doing terrific, and she will most likely teach big data. So you will not see me teaching big data most likely anymore. But if you're curious about how the course goes, check YouTube. And there are more AI courses, like I mentioned, deep learning. There's also an AI seminar still coming in the AI bachelor's, and there's an autonomous robots course. So there are lots of opportunities for you to learn more about AI with regards to deep learning, autonomous robots, but also commercialization. Now, we finished the content, and I will say a few words about the projects. We've done a lot of lectures in a couple of weeks. I know this. And it was lots of content. It was probably pretty tough to understand all of this. I told you the course is very ambitious, but there's no written exam, but rather projects. And the main workload will be from now on your projects. And the projects are in the second half of the term. You will work on a project on any topic related to vision. It's your choice on projects or in groups of 3 to 4 students. And it's only 3 to 4, not 1, not 2, not 5, so no exceptions. And I also said you need to register for this exam in Primus. And for any questions on Primus, ask the Center for Studies, because I'm not involved in there. You have already picked your robot, and now end of April, we have the last lecture. And I want you to finalize your project topic. And I've sent you an update in iLearn a few weeks ago that starting tomorrow, the 25th, you can add your project topic in iLearn. And what you would put is your project topic, just the name of the topic, and you would submit all the names and student IDs of your group members. It's important one submission per group. And I learned, please not multiple submissions per group. And you need to submit this until Friday, the 9th of May. And the deadlines are binding. So don't be late with the submission. I will, after May the 9th, review your submissions. And on May 15, so you now have a few weeks to think about your projects. So we will not have a lecture next week because next week you're supposed to think about your project. Next week, Thursday is anyway a public holiday again. That's why we did a lecture last week on the public holiday that we are finishing today, so you have enough time for your projects. You also can think about your project on May the 8th still, because I will be away in that week at a conference. And then May the 9th is the deadline to submit your topic and your names and student IDs. I will review this after May the 9th. And then on May 15, we will meet online already starting 8 o'clock, because we will have lots of groups, because I expect we have 80 groups. And each group will meet online in Zoom, and each group would briefly present their proposal. But really only 1 to 2 minutes per group, just what you want to do. And it's very important you join this meeting because you need to present your proposal. You need to stay for the other proposals because you need to see if any group has something related or similar questions. So please, only 1 or 2 slides of what you want to do and a brief structure. And if you talk more than 2 minutes, I will interrupt you because we have 80 groups that want to present, and it would take very long, and that's why we're already starting at 8, so we're not running out of time at 1 p.m. And you will present in the order in which I mentioned these group projects. So you submit everything until May the 9th. I will review it, and then I put a list in Nextcloud with all your submissions. You will review the list. I will notify you then. And it could be, maybe some name is wrong or something didn't get copied properly. So if you need any corrections to this list, you would tell me, and you would then present on May 15 your proposals. The actual project presentations, they will get marked, or your project will get marked, and they will be on June the 28th and 29th, so a Saturday and Sunday, as well as July the 5th and 6th. Because we have too many groups, we need to do this on 2 weekends. But you are unable to choose a specific day or time. You're simply supposed to be available, and I'm unable to, because I'm getting a lot of emails, students telling me they're on vacation or whatever. This will take place on 2 weekends, and you're supposed to be available because it's during the term, and I'm unable to accommodate any exceptions or online presentations. All of this only takes place on campus. And once I have the list of projects, I will also determine then on which days these presentations takes place. But this will follow later. We first need to collect your topics and your names. So end of June and actually early July, because we have last year we tried it on 1 weekend, which was very painful. It was a Saturday and Sunday, each from 8 a.m. to 10 p.m. or even later. So that doesn't work. So we need to do 2 weekends because this year it's even more students. And I've checked, yeah, it's 250 students. Last year it was 230 students. So we also keep growing. And after the presentations, there would also be a date for you to return your robots, but you'll be notified. Now, your project will get marked. You can score up to 50 points, and 50 points will be a 1.0. 49 points will be a 1.1, 48 points a 1.2, but the valid marks are only 1.0, 1.3, 1.7. So if you score 44, it's a 1.6, which is not a valid mark. So I always round this to your advantage. And if you score, I don't know, 37 points is a 2.3, and that's a valid mark, but 38 is a 2.2, which gets rounded to 2.0. Your presentation as a group should take 15 minutes and don't present substantially longer or shorter. There will be a Q&A session following your presentation, and the Q&A session would not only address your actual project, but maybe some of the content of the lecture as such, because I've noticed in the last few years some students don't follow the lectures, they only try to work on the projects, and the lectures are important. I will not quiz you in the Q&A on little details from the course, but maybe just to make sure you've attended a lecture and you know what the content is about. So we have a 5-minute Q&A session, and the groups will present together for 15 minutes. So the whole group in total presents 15 minutes, and then we have a Q&A session. Your mark will be up to 50 points. What I want initially in your presentation, briefly explain what's the motivation of the topic. Why have you picked it? Why do you like it? Why do you think it's relevant? Up to 5 points. Then you would present your methodology. So what you have done and the underlying algorithms, the maths or background. You don't need to revise all the details from the lecture. That's what we had the lecture for. But if there is something you feel that needs to be revised, do so, but focus on the actual methodology that you have done. This is up to 15 points. And then I want to see a demo. I want to see stuff that is actually running. And this is another 15 points. Ideally, this would be a live demo that you show us that something on your computer or a robot, but always feel free to have a backup video because sometimes live demos don't work because something broke or a robot broke. Or once I had some students who built some big robot at home that they couldn't take on campus. But for things that can be shown on campus, I want to see a live demo and a backup video only as a backup. Then you would also present briefly lessons learned. So you would present what has worked in terms of the methods and what has not worked, because we discuss all this theory and it all looks great. But sometimes this stuff doesn't work as expected, maybe based on your data or some constraints. So you would also tell us a little bit about the lessons learned. So focus should be your methodology and the demo in these 15 minutes, plus the motivation and briefly lessons learned. And then you can get up to 10 points for the Q&A. So in total, you can get 50 points for the mark. And in the next few weeks, whatever questions you may have, say about the project topic, get in touch by email. We can meet on campus or online. And if you face some issues with your project during the term, something is not working, or you'd like some initial feedback, feel free to send an email or we'll make an appointment, and I'll be happy to help. For all the robot-related problems, please get in touch with Mr. Runkel. He's happy to assist with the robots. So, are there any questions from you? If so, maybe just raise your hand here in Zoom or some reaction. If and then turn on your mic, or I'll wait for you and see if you have any questions. So there don't seem to be any questions as it looks. So we're okay then. And I wish you all the best for finding group and projects. And there's one question here about algorithms and data structures. One student wants to register for the exam, and you need to, so algorithms and data structures is a different course. And there you also need to register for this mandatory problem. And if you don't find this in Primus, please ask the Center for Studies, because it's 2 examinations in algorithms and data structures. And I don't have access to Primus, so the Center for Studies will be most happy to help with any issues, how to register for exams. I'm unable to assist with this because I don't have access to the portal. So, with there not being any further questions, I wish you a good afternoon and all the best for the next few weeks in the projects. One student wrote here that there seemed to be some issue on Primus with registering, but yeah, Center for Studies will be happy to help. I don't have access. So take care and see you soon. Bye bye.